Mathematics, Faculty of Science and Technology, University of Airlangga. Operating since 1982, the undergraduate program of Mathematics University of Airlangga has a vision to be a leading study program in Indonesia and recognized at the regional level in the development of mathematics and its application, especially in the field of life sciences and industry, as well as play a role in the development of a scientific community that has religious morality. In achieving this vision, the undergraduate program of Mathematics University of Airlangga has missions: manage learning and teaching excellence in mathematics and its application, supported by competent resources. Participate in the development of research in the field of mathematics and application that support the improvement of the quality of education, knowledge, and social welfare. Conduct community service activities in the field of mathematics and its application through mutually reinforcing cooperation with the elements of society, industry, and education. At this time, the undergraduate program of Mathematics University of Airlangga had obtained ASIN accreditation from BINPT. There are 4 scientific fields in the undergraduate program of Mathematics University of Airlangga, including algebra, analysis, systems modeling, also operation and computing research. As the primary means of learning, the mathematics department classroom have been equipped with an LCD projector and a large room capacity. Besides that, the mathematics department also has a computer laboratory to support learning in the form of practice. The undergraduate program of Mathematics University of Airlangga is classified as active in participating in conferences and competition, such as scientific writing competition, the student creativity program, etc. Not infrequently, students in mathematics have won awards in international competitions. In addition to honing academic skills, there are also media to hone students' non-academic abilities through activities held by mathematics students' organizations of Himatika, such as MLC Math and Logic Competition, Himatika Mengabdi, Himatika Balance, Community, API, magazines, etc. Go ahead and do your work and achievement in the Faculty of Science and Technology undergraduate program of Mathematics University of Airlangga. Welcome to the undergraduate program of Mathematics, Department of Mathematics, Faculty of Science and Technology, University of Airlangga. Operating since 1982, the undergraduate program of Mathematics University of Airlangga has a vision to be a leading study program in Indonesia and recognized at the regional level in the development of mathematics and its application, especially in the field of life sciences and industry, as well as play a role in the development of a scientific community that has religious morality. In achieving this vision, the undergraduate program of Mathematics University of Airlangga has missions. Manage learning and teaching excellence in mathematics and its application, supported by competent resources. Participate in the development of research in the field of mathematics and application that support the improvement of the quality of education, knowledge, and social welfare. Conduct community service activities in the field of mathematics and its application through mutually reinforcing cooperation with the elements of society, industry, and education. At this time, the undergraduate program of Mathematics University of Airlangga had obtained ASIN accreditation from BINPT. There are 4 scientific fields in the undergraduate program of Mathematics University of Airlangga, including algebra, analysis, systems modeling, also operation and computing research. As the primary learning, the mathematics department classroom have been equipped with an LCD projector and a large room capacity. Besides that, the mathematics department also has a computer laboratory to support learning in the form of practice. The undergraduate program of Mathematics University of Airlangga is classified as active in participating in conferences and competition, such as scientific writing competition, the student creativity program, etc. Not infrequently, students in mathematics have won awards in international competitions. In addition to honing academic skills, there are also media to hone students' non-academic abilities through activities held by mathematics students' organizations of Himatika, such as MLC Math and Logic Competition, Himatika Mengabdi, Himatika Balance, Community, API, magazines, etc. Go ahead and do your work and achievement in the Faculty of Science and Technology undergraduate program of Mathematics University of Airlangga. Welcome to the undergraduate program of Mathematics, Department of Mathematics, Faculty of Science and Technology, University of Airlangga. Operating since 1982, the undergraduate program of Mathematics University of Airlangga has a vision to be a leading study program in Indonesia and recognized at the regional level in the development of mathematics and its application, especially in the field of life sciences and industry, as well as play a role in the development of a scientific community that has religious morality. In achieving this vision, the undergraduate program of Mathematics University of Airlangga has missions. Manage learning and teaching excellence in mathematics and its application, supported by competent resources. Participate in the development of research in the field of mathematics and application that support the improvement of the quality of education, knowledge, and social welfare. conduct community service activities in the field of mathematics and its application through mutually reinforcing cooperation with the elements of society, industry, and education. At this time, the undergraduate program of Mathematics University of Erlangga had obtained ASIN accreditation from BNPT. There are 4 scientific fields in the undergraduate program of Mathematics University of Erlangga, including algebra, analysis, systems modeling, also operation and computing research. As the primary means of learning, the mathematics department classroom have been equipped with an LCD projector and a large room capacity. Besides that, the mathematics department also has a computer laboratory to support learning in the form of practice. The undergraduate program of Mathematics University of Erlangga is classified as active in participating in conferences and competition, such as scientific writing competition, the student creativity program, etc. Not infrequently, students in mathematics have won awards in international competitions. In addition to honing academic skills, there are also media to hone students' non-academic abilities through activities held by mathematics students' organizations of Himatika, such as MLC Math and Logic Competition, Himatika Mengabdi, Himatika Balance, Community, API, magazines, etc. Go ahead and do your work and achievement in the Faculty of Science and Technology undergraduate program of Mathematics University of Erlangga.
The need for experts with higher competence is increasingly needed along with the development of the era in the era of technology and information. Erlangga University is one of the leading universities in Indonesia, which has a focus on preparing future experts so that it becomes the campus of choice for scholars who have completed their studies. Therefore, in responding to this challenge, especially in the field of mathematics, the university opened a master's program in mathematics under the auspices of Mathematics Department of the Faculty of Science and Technology so that this study program contributes to the development of the university.
Assalamualaikum warahmatullahi wabarakatuh. Hi, my name is Dr. Nur Hamida. I am a coordinator of Mathematics Master Study Program, Faculty of Science and Technology, Erlangga University, Indonesia. Mathematics Master Study Program, Erlangga University was established on 16 June 2021 and has accepted students for the first time in 2022. The vision of Mathematics Master Study Program Erlangga University is to become a center for development of mathematics and its application in the field of life sciences based on religious morality. The Mathematics Master Study Program Erlangga University offers 2 study paths, namely by course and by research.
My name is Faisal Farah Hertiko and I'm one of the Mathematics Master student at Erlangga University who takes the research curriculum. I think in this curriculum, we are given more flexible time in terms of lecture. because this curriculum is designed for someone who already have a job or a lot of activities and unable to attend regularly. Moreover, there are still few research-based master program in Indonesia. So, the Airlangga University, one of the prestigious university, open option with this curriculum on master program of mathematics. With adopted the lecture capabilities, I was very confident to continue my studies here.
Hello, my name is Abena Pakbar. I'm from Master Program of Mathematics at Airlangga University, who takes Modeling and Simulation Expertise Group. What made me sure to continue my master's degree here was the very affordable cost of studying here and the quality of the lecturers who were highly qualified because they always produce a lot of work or publication. Apart from that, the lecturers here was very friendly and always motivated their students to study enthusiastically and achieve their goals. The curriculum that I chose was by course, considering that I am a fresh graduate who has not worked yet, so my time to attend lectures here has become more flexible. Thus, I can develop existing knowledge so that later I can apply it in my life.
Hi, my name is Kartini Putri Ulandari and I am one of student of Mathematics Master at Airlangga University who takes research curriculum.
I think in this curriculum, we are given more flexible time of lecture because in this curriculum is designed for someone who has job and a lot of activities who does not have to attend the lecture. And now, I'm already work at the PT Bank Mandiri. However, this curriculum is perfect for me who has already have a job and already have a family, so that I have a flexible time to work and study master degree and to have time with my family. Moreover, there are still a few universities that have opened the master study program with research curriculum.
The study program offers 5 areas of interest, namely analysis and geometry, algebra and combinatoric, system modeling, operation research and computation, and statistics. The study program has facilities that meet national and international standards, including cool lecture rooms, laboratories, discussion room, reading room with textbook and journal, Wi-Fi, and software.
The Master of Mathematics study program at Airlangga University is committed to producing graduates who are able to meet the demand of the time as a dynamic for achieving better quality education.
For those of you who prioritize quality, please come join with us. Register yourself as a student of Mathematics Master Study Program Airlangga University, Indonesia. We offer proof, not promises. The Mathematics Master Study Program Airlangga University, Indonesia. Mathematics develop life science and technology. Thank you. Wassalamualaikum warahmatullahi wabarakatuh. Mathematics Master Study Program Airlangga University. Mathematics develop life science and technology.
Greetings from Universitas Airlangga, a prestigious educational hub in Indonesia that thrives on academic brilliance and pioneering research. We extend our warm invitation to unlock the realm of knowledge and innovation at the Faculty of Science and Technology.
Faculty and Administration, Fundamental and Applied Science, Sustainable Development.
FST Universitas Airlangga was founded in 1982 as the Faculty of Mathematics and Natural Sciences. Afterwards, it has evolved to become a leading center for science and technology education. This faculty is committed to provide students with the skill to succeed in the future.
FST Universitas Airlangga offers a dynamic and diverse academic community with multiple departments and 13 specialized programs. providing students with in-depth knowledge and practical skills in fields ranging from engineering and computer science to natural sciences and biotechnology.
At the Faculty of Science and Technology, our utmost priority is to provide a high-quality education that empowers students with the knowledge and skill to excel in their chosen fields. To achieve this, we have assembled a team of expert faculty members who are not only accomplished in their respective domain, but are also deeply passionate about teaching and conducting cutting-edge research. Through the dedication and guidance, our students receive a transformative learning experience that prepares them for the challenges and the opportunities of the ever-evolving worlds of science and technology.
Our modern laboratories provide the necessary equipment for students to develop practical skills that are highly sought after by employers. Additionally, we foster a supportive and inclusive environment where students can thrive, ensuring they are well prepared for future challenges. We foster a culture of research and development in the fields of science and technology by offering diverse research activities. Students are actively encouraged to participate in groundbreaking research endeavors that address practical challenges faced in the field. Beyond academics, we strongly promote engagement in student activities. Students are encouraged to become involved in a wide range of activities, such as student organizations, seminars, workshops, and social events. These experiences facilitate the development of crucial social skills, leadership qualities, and networking capabilities.
Our ambition knows no bound. We are transforming education into a global innovation hub, cultivating leaders who pioneer solutions for humanity challenges. Industry collaborations, internship, and cutting-edge technology empower our graduates to excel worldwide. Partnering with prestigious institutions globally, we drive interdisciplinary research and exchange programs. Together, we'll push the boundaries of science and technology, leaving an enduring impact on our society. The Faculty of Science and Technology at Universitas Airlangga has produced many graduates who have gone on to become leaders and innovators in their respective fields. These graduates have held prominent positions in industry, government, and academia, and their work has had a lasting impact on the world through their groundbreaking research and innovative solutions.
Whether you dream of becoming a pioneering scientist, a tech innovator, or an engineering trailblazer, the Faculty of Science and Technology at Universitas Airlangga is the perfect place to turn your aspirations into reality. By nurturing and empowering future leaders in various scientific and technological fields, the faculty contributes to the growth of cutting-edge industries that address society's pressing challenges.
Faculty of Science and Technology Universitas Airlangga, the best science with morality.
Lagi, gua buka player chat buat kalian yang
All right, everyone. Okay, everyone. So today we have guest lecture meeting. For everyone, we have 52 participants here, including the committee. All right, without any further ado, let's get started. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh.
Salam.
Good afternoon, ladies and gentlemen. Welcome to today's guest lecture on application of bifurcation analysis to epidemiological models. My name is Akbar, and it is truly an honor for me to serve as your master of ceremony this afternoon. To begin our event, let us express our gratitude to Allah Subhanahu wa Ta'ala for His blessings that allows us to gather here today in good health and spirit. Before we start, I'd like to extend a warm welcome to all distinguished guests, especially Professor Dr. Fatmawati, Master of Science, Vice Dean 3 of the Faculty of Science and Technology, our honorable speaker, Dr. Chinwendu Emilian Madabweze, Doctor of Philosophy, as well as the moderator for today's lecture, Mr. Rudianto Artiono, Master of Science, and also respected lecturers and all participants joining this academic session. To begin the ceremony, let us stand and sing together the Indonesian national anthem, Indonesia Raya. All right, thank you everyone. Next, we will have the opening remarks from Professor Dr. Fatmawati, Master of Science, Vice Dean 3 of the Faculty of Science and Technology. To Professor Fatmawati, we can invite you to deliver remarks. The time is yours.
Okay, thank you, Mas Akbar. Assalamualaikum warahmatullahi wabarakatuh. Honorable Professor Chinwendu Emilian Madubese, PhD from Department of Mathematics, Joseph Sarwan Tarka University, Makurdi, Nigeria. Honorable lecturer, student, and all participants, good afternoon, ladies and gentlemen. First of all, I would like to express my gratitude to all of the participants and distinguished guests, Professor Chinwendu, for your contribution to the mathematical modeling webinar with topics application of bifurcation analysis to epidemiological model. I hope that all of the participants here will find a lot of experience and insights into the application of infectious disease modeling in the real life. Ladies and gentlemen, through this webinar, I hope our collaboration can be continued, especially in education, such as a webinar today, joint research, and also joint community services, because collaboration is an essential component for us to move forward to face the global challenges of becoming a world-class university. Perhaps that is all from me. Once again, thank you to the speaker and to everyone. Please enjoy today's webinar. Wassalamualaikum warahmatullahi wabarakatuh.
Thank you very much, Professor Panawati, for the inspiring words. Before I hand the session over to our moderator, please allow me to once again acknowledge our distinguished speaker, Professor Chinwendu. Good afternoon, Professor.
Good afternoon.
Thank you so much. It's an honor to have you with us today.
Thank you.
Okay, next we will listen to the opening speech and introduction of our guest speaker by the moderator, Mr. Dianto Artiono, Master of Science. To Mr. Dianto, the time is yours.
All right, okay. Thank you, Mr. Akbar. Can you hear my voice clearly, Mr. Akbar?
Yes, Mr.
All right, okay. Right, okay. Good afternoon, everyone. Assalamualaikum warahmatullahi wabarakatuh. First of all, on behalf of the organizing committee of the Faculty of Science and Technology at Erlangga University, I would like to extend my warmest greeting to all participants who have taken the time to register and join this afternoon guest lecture. First, I would like to introduce myself. My name is Rudianto, and this afternoon I will be serving as the moderator for our guest lecture session. Actually, it is a true privilege to introduce our distinguished speaker, Dr. Chinwendu Emilian Madubuizi from the Department of Mathematics, Federal University of Agriculture, Makurdi, Nigeria. And this is the second time for Dr. Madubuizi give a guest lecture in our faculty. We really appreciate for that, Dr. Madubuizi. Thank you so much.
Thank you.
All right, okay. So before we begin the lecture, allow me to read a short version of Dr. Madubuizi curriculum vitae. Okay, here, Dr. Madubuizi is a mathematical epidemiologist with a background in infectious disease modeling and computational simulation. Her research interests mainly focus on mathematical ecology, zoonotic disease, and neglected tropical disease. She utilized differential equation, uncertainty analysis, and simulation technique using tools such as Python and MATLAB to analyze disease dynamic and assess intervention strategies. Her goal is to apply multidisciplinary research to have a tangible impact on public and animal health policies, bridging data-driven approach with mathematical modeling for effective decision-making and epidemic preparedness. Dr. Madubuizi earned her bachelor degree in industrial mathematics obtained in 2010 and master degree in mathematics obtained in 2012 from University of Benin, Benin City, Nigeria. And she holds her PhD in mathematics obtained in 2018 from Federal University of Agriculture, Makurdi, Nigeria. She has extensive teaching experience and has been involved in guiding students in both undergraduate and postgraduate program. And currently, she serves as an applied mathematics lecturer at the Federal University of Agriculture, Makurdi, Nigeria. She has authored and co-authored numerous publications in reputable journal and has been actively engaged in advancing mathematical approach to public health problem, particularly in infectious disease modeling. And her work highlights the use of nonlinear dynamical system to understand the disease transmission and control strategies. And today, she will deliver a lecture entitled Application of Bifurcation Analysis to Epidemiological Model. Before we begin, let's have a little chat with Dr. Madhubuisi. Dr. Madhubuisi, how are you today? Are you okay for today?
Yes, yeah, I'm okay. I'm
All
okay.
right,
Yeah,
that's
I'm
good.
okay.
Okay. What time is it now in your country, Dr. Madhubuisi?
Some minutes after 7 in the morning.
All right. Oh, hopefully it's not too early for you, Dr. Madhubuisi. All right. Okay, great. Anyway, thank you so much for your time and for sharing your expertise with us. And it is really our pleasure to have you for the second time with us today. So, Dr.
Thank you.
Madhubuisi, you have 1 hour to do presentation and then 50 minutes for question and answer session afterward. Is that okay for you?
Ah, I will try. It's okay. I will try
Oh.
within 1 hour. I will try.
Yeah. All right. I will remind you if we have limited time for it. That's all right. Okay. Okay. Without further delay, please welcome Dr. Chinwendu Emilian Madhubuisi. Doctor, the screen is yours.
Thank you. Thank you,
Okay.
everyone. I'm going to share my screen. Can you see my screen?
Yeah. Is it clear?
Okay. Yeah, so I'm trying to take you to the beginning. Okay. Sorry, what is going on? To the end. Okay. Thank you very much, and good afternoon, and good morning, good afternoon.
All right.
Yeah, for joining this meeting. Okay, as you have introduced me, my name is Joseph Sawantaka University. That's what the university is now. Formerly University of Agriculture, Bifurcation Analysis Technological Models. I just want to say, first of all, thank you to Fatiwati, Professor Fatiwati, for the continued collaboration. I undergo a postdoc program in this institution too in 2023. And ever since then, I also continue collaboration with Professor Fatiwati. So this is my second time of giving lectures in your university. So it's a privilege to be part and be collaborating with your institution. So today, going by our topic, I'm going to present application of bifurcation analysis to epidemiological models. So why are we talking about bifurcation analysis to epidemiological models? Because bifurcation is kind of something that causes a chaos, so which can actually happen when there is a small changes in parameters. But before we can define what is a bifurcation analysis, we need to define what is epidemiological models. Epidemiological models are mathematical models used to analyze the spread of disease. It predicts the progress of outbreak and also support impact assessments, planning and policy decisions. Because when you use a mathematical model to analyze disease, it helps you to understand the dynamics of that disease and also help you to know which control to implement in order to bring down the disease, which you can also notice very well during COVID, what mathematical model have done to controlling of disease. So these models have become an important tool for understanding the quantitative analysis, controlling the spread of the disease. Yes, because if we if we develop a model without trying to carry out the quantitative analysis of it, we cannot actually find out which parameters of the model actually control the disease. So the quantitative analysis of the disease also helps to understand, to control the spread of the disease. Then many of the epidemiological models have a strong non-linear terms. So therefore, sometimes they may exhibit a bifurcation properties. So that is essence of what we want to look at today. Now, what is a bifurcation definition? Bifurcation phenomena happen when there is a small change in the system parameter values, causing a topological changes in the system behavior. What it means that if I have my parameters of the model, when there is a little change in one of the parameters of model, it may change the dynamics of that system. And so this system is a system of ODE. Sometimes they can be partial differential equation, but particularly in this lecture, we are going to consider only differential equations, ordinary differential equations. So as a result of these small changes, these small changes can change the stability of equilibrium state of the dynamical system. The equilibrium point is a state where the system is not changing. And we need equilibrium state in order to determine whether there is a stable system or unstable system. Stable system in the sense that when there is a small shift in the equilibrium, does it return back to its original state or does it move away from original state, which results in instability? Now, this bifurcation can also lead to a major shift in the course of it can lead to a major shift in the course of an epidemic, in the sense that when there is this interchange of stability of equilibrium points, for example, from disease-free to endemic equilibrium, that means it has actually affected the control of that particular disease. This parameter can also influence the eigenvalues, because most of this bifurcation is determined by the eigenvalues of the system. Now, eigenvalues is what we use to determine the stability of our system. Now, the point at least, and it occurs at the point where at least one of eigenvalue have a zero real part. So that part is what we call bifurcation point. From there, we can now analyze what kind of bifurcation do we have and what kind we don't have. And this theory also helps us to understand how disease spread, especially during the major public health events. And the course of this lecture, we'll see that we have this threshold, which we call basic reproduction number, which we are told that when it's less than 1, there is a tendency that disease will control. But when there is a bifurcation, even when it's less than 1, especially in backward bifurcation, there is a tendency that disease cannot be controlled if other controls are not implemented. So that is where the bifurcation analysis is very important in disease modeling. Now, we cannot talk about bifurcation analysis if we don't talk about what is the reproduction number, the threshold quantity, which we call Adoma arrow naught. During the COVID, many people heard about arrow naught. Arrow naught is actually a threshold quantity, which helps us to determine whether a disease will be controlled, whether it cannot be controlled. It is the average number of secondary infection period when introduced in
Really sorry, Dr. Shinwendu, I think we lost you. Sorry.
Perhaps, Dr. Chinwendu, you can off your camera.
Sustainable population. What it means that is a number when there is no infection in the environment and one person is introduced in the environment. So we want to know, is this going to spread when that one person? My screen still sharing.
Yeah, I think we lost your screen, and now we lost you as well.
Okay.
All right. Okay.
Can you hear me?
Yeah, you can try pause. Yeah. It's fine. Maybe you can try pause share the screen again, Dr. Chinwendu.
Yes, I'm sharing the screen again. Can you see the screen?
Okay.
So when it's greater than 1, it means
okay. Yeah, it's okay now.
So when it's greater than 1, it means that disease can be maintained in the environment, which will lead to a stable endemic equilibrium. Endemic equilibrium is when there is a disease in the environment. So in a situation where the infected population is present in the environment. Now, we have different types of bifurcations. We have a local bifurcations, we have a global bifurcation. Actually, in this course, we are going to consider only local bifurcations that is mostly used in disease epidemiology because it has to do with the local stability of equilibrium states. So this is analyzed through the changes in local stability properties of equilibrium, periodic orbit, or invariant state as a parameter courses through a critical threshold. Now, this critical threshold can be determined during your quantitative analysis. Now, global is more like a larger invariant state, so which can collide with each other or with equilibrium of the state. It cannot be dictated purely by stability analysis of equilibrium, which is fixed point or equilibrium point. Now, the types of local bifurcation, we have saddle node bifurcation, we have transcritical bifurcation, we have peak fold bifurcation, we have hub bifurcation, we have forward and backward bifurcations. So these different bifurcation has their own different meaning, but sometimes some of their meaning can collide with each other. So we have that southern node bifurcation is a collision or disappearance of two equilibrium in a dynamical system. This occurs when the critical equilibrium have 1,0 eigenvalue. The transcritical bifurcation is distinct by the equilibrium state, where the real part goes through 0 and cause an exchange of stability of equilibrium state when R naught is equal to 1 at bifurcation parameter beta equals to beta star. Now, what happened here is that at R naught equals to 1, there is a change of stability, a change of stability. Maybe R naught less than 1 from which is it has to do with stability of disease free, R naught greater than which it has to do with the stability of endemic equilibrium. So at that critical point, R naught equals to 1, there is a change of stability of equilibrium. So that leads to transcritical bifurcations. Now we have hub bifurcations. Hub bifurcation happens when the linear system have at least one eigenvalue with a 0 real part that is purely imaginary. So, for example, we have our eigenvalues. Our eigenvalue is equal is
Sorry, Dr. Chirwendo, I think we lost you again. Yeah. Really sorry, Dr. Chirwendo. Are you still with us?
contain both real parts and imaginary parts, which we say that the real part determines equals to 0, and the imaginary part is pure to determine the bifurcation of bifurcation.
Really sorry, Dr. Chewendo. I think we lost you because you share the screen. Is that okay if we share the material? Dr. Chewendo. Hello, Dr. Chinwendu. I think we lost Dr. Chinwendu, so really sorry for all the participants that we lost our guest lecturer. Maybe we have to wait for about 2-3 minutes.
Dr. Chinwendu masih di Zoom sebetulnya.
Oh, ada, Bu.
Iya. Atau slide-nya dari panitia saja ya?
Iya, Bu, kita tawarkan.
What happened?
Hello, Dr.
Yeah.
Chinwendu. Is that okay if we share the material? So we share the material from us, so you just explain about the material. Is that okay?
It's okay. It's okay.
Yeah, okay. So Akbar will
I
share
think it's
the...
with yeah, it's with
Yeah, all right, okay.
Okay, thank you. Okay, so now we have different. The next slide. The next slide.
Yeah, okay.
So we have, this is the diagram of the different bifurcations we have. This is southern node bifurcation, which we see as it's caused by the real part of the infected population. We also have the transcriptal bifurcation. You can see that the line is straight, meaning that there is the exchange of a stability of equilibrium. Then we have a pitchfork bifurcation, which is also given as what we have here. The next slide. So now the forward bifurcation is a phenomenon where the disease-free losses its stability and a stable endemic appear as arrow crosses through one. What it means forward bifurcation here, when you have a forward bifurcation, it means that a disease-free is locally stable if arrow naught is less than 1. Also mean that the endemic equilibrium is locally stable if arrow naught is greater than 1. So what it means that from the disease-free, it lost its bifurcation as it's crossing towards 1. So that is what there you now have a stable endemic equilibrium. And now this forward bifurcation have different characteristics. The first one is that the absence of positive endemic equilibrium near the disease free when R naught is equals to 1. And so what it means that when R naught is less than 1, it's only a disease free that is locally stable. Then it also have a low level of endemicity when R naught crosses slightly above 1. So when you see the diagram, when it crosses slightly above 1, the endemic situation is very low. Now, when a forward bifurcation happens, there is a possibility there is a global stability of disease-free equilibrium and endemic equilibrium. So that is also what also the condition also implies too. When you have a forward bifurcation, it means that your disease-free equilibrium, there is a possibility it can likely be globally stable, and your endemic equilibrium can likely also be globally stable when R naught is greater than 1. The next slide. Now, we have a backward bifurcations, which happens when the local stability of disease-free equilibrium coexist with endemic equilibrium, even when R naught is equal to 1. So what it means that we say that when R naught is less than 1, the disease can be controlled. But in a backward bifurcation, R naught less than 1 is no longer enough to eradicate the disease in the environment. So meaning that another control can be implemented in order to reduce further, to avoid the endemic situation in the population. So in a backward bifurcation too, once basic production number causes unity, disease can invert to a higher endemic level in the environment. So decreasing the reproduction number to a former level will not actually reduce the disease, make the disease to disappear in the environment. So that means that the other implications, other intervention can be applied so that the reproduction number can be reduced more further in order to control the disease in the population. The next slide, please. So this is what you have as the diagram. This is a forward bifurcation. If you look at the forward bifurcation, the blue started from the blue line started from the 0. That is where you have a disease-free equilibrium. But disease-free equilibrium means there is no infection in the environment. Now, this diagram is making use of force of infection, which contains the infected population. So that blue one shows that when it's between 0 and 1, you have a 0 disease. Now, when it's slightly above, greater than 1, you cannot see that it now leads to stable endemic equilibrium, which implies that R naught is greater than 1. Now, for what we have, the screen, I cannot see the screen.
It's visible for the screen, Dr. Chinwendo.
Okay, so we now have this is a backward bifurcation now. See the way the bifurcation happens. Even when R naught is less than 1, the endemic equilibrium still exists, which has to do with the red dotted line. So even in less than 1, there is endemic situation because you can see that it's no longer at 0. It's no longer at 0, so there is endemic situation, which also covers even within the 1. So, and this endemic situation here is very, very high compared to when you have it in a forward bifurcation. So that is different between the forward and backward bifurcation based on the diagram we have here. The next slide. So, and another thing, there's also further implication of this. Further implication of this is that when you have a backward bifurcation, there's a tendency you have a subcritical transcritical bifurcation at R naught equals to 1. You also have a saddle node bifurcation at R naught equals to a critical value of R naught less than 1. Then also in the neighborhood of 1, that is the neighborhood of R naught equals to 1, there is a stable disease-free equilibrium existing with 2 endemic equilibrium. So meaning there is an unstable small equilibrium and a stable larger endemic equilibrium. Now, the 2 endemic equilibrium can actually vanish through saddle node bifurcation when the bifurcation number falls between the critical bifurcation number, which is less than 1. Now, for R naught greater than 1, there are 2 equilibrium states: unstable disease-free equilibrium and stable endemic equilibrium. Now, when R naught is very close to unity, that is 1, disease control depends only on the initial size of the subpopulation in the model. What this one means that in a forward bifurcation, we say that when a system exhibits a forward bifurcation, there is a tendency of global stability. Now, tendency of global stability means that the control of the disease does not longer depend on the initial size of the population. Now, for the backward bifurcation, the initial, because the system exhibits a backward bifurcation, the control of disease still remain on initial size of the subpopulation of the model. Now, reducing R naught below the critical bifurcation value, which is R naught saddle node can lead to a disease eradication if the disease free is globally asymptotically stable. The next step, the next slide. Now, for us to actually look at the quantitative analysis of this, we have different mathematical tools we use. And one of these different mathematical, of course, our model is our disease model, we are using a ordinary differential equation. So consider ordinary differential equation, which is given at equation 1. So where the S1, S2 to Sn are the subpopulation of the model. Now, derivative of S1 to Sn, just like if your model is divided into different compartments. So we will have a system of equation given at this equation 1. The next slide. So also then for us to carry out the other local bifurcation, which is saddle node bifurcation, transcritical and pop-fork bifurcation, we use this particular criteria, Sotomayor criterion. What it says is that if I have my system of equation in which the right hand side, which is f of s star mu 0, then this s star, it can be your disease-free problem. The mu 0 is the bifurcation parameter. Then the matrix which I got by Jacobian matrix has a simple eigenvalue which is equals to 0, corresponding to S eigenvector. Then the transpose of that matrix, which is AT, has another eigenvector which corresponds to the eigenvalue equals to 0. Now, if I have a condition which obeys this equation 2, it means that I have that particular bifurcation parameter, which is I choose as mu equals to mu 0, has a saddle node bifurcation, that system. So what it means that the first one, we take the transpose of the eigenvector and multiply it by f subscript nu. F subscript nu is partial derivative of that particular right-hand side of the equation in respect to the bifurcation parameter. Then why the second one, the second derivative of is a more like a Hassan matrix. It's not a Jacobian matrix. Hassan matrix, which can also go into show how to derive that too. The next slide. Now you have a transcritical bifurcation when it obeys these third conditions. So meaning that the first one, when is equals to 0, the second one is not equals to 0, the third one is not equals to 0. Now, if for instance you are doing the first one is not equals to 0, that means it cannot obey transcritical bifurcation. This is an error from what they updated in this saddle node bifurcation. Right.
Dr. Chewendo.
The next slide.
Yeah.
Are you with me? The next slide. So the next, this is the condition we have for pitchfork bifurcations. Once it obeys these 4 conditions, it means that we have a pitchfork bifurcation that's mu equals to mu 0. So the next slide. So now for us to determine the second derivative, the Hassan of a vector field, we have it that, okay, this is the equation 5, this f of x, capital F of s, it has to do with the right hand of the ODE that you have. So once we have the right hand of the ODE that we have, so we have this matrix, vector matrix that we have here in equation 5. Then the next slide. So when we have it, we are going to compute the Hassan vector, which is a combination of the Hassan of each of components of Fi. That is a Hassan tensor with the shape m n by n. So what it means that if we have up to m, so each of them have S1 to Sn. That is what produce that n comma n. So I have to get this combination vector. Capital H subscript capital F will give me a combination of each of them for 1 to m. M in the sense that it's up to m. So for example, so each of them is going to produce m by m. So if for the first one, take the second derivative, respect to each of the state variables, until I get up to this. Then for me to get hf multiply with vector v comma vector, I'm going to have this the last term, which is given as this. So that will help us to determine that d squared, the second derivative, which is going to produce a Hassan vector, because it's not a scalar multiplication in that case, it's a vector multiplication. The next slide. So that is for the local bifurcation. Now we look at the forward bifurcation. There's this method that we use, center manifold approach, which is given as this and the next slide. So what this particular means that S dot, which is S derivative, is equals to what I have the right hand side, which is like ODE that we use to your model of a disease, which is in form of ODE. So we now say that if we assume that S naught is equals to 0, S naught equals to 0 is an equilibrium for that equation 7. Now that S naught equals to 0 can be a disease-free equilibrium. Now if we can determine A, which happened at disease-free equilibrium, is analyzing around the S naught equals to 0, then we have a 0 simple eigenvalue. Then where other ones have a negative real part, then that matrix will find the right eigenvector, we find the left eigenvector corresponding to 0 matrix. Now if we can compute A and B, the next slide, which is given as this, the next slide. So then we can now say, and these conditions are established. There are many of these conditions which leads to negative, positive stability. But what now leads to a forward and backward bifurcation is that when we have a forward bifurcation, when A is less than 0 and B is greater than 0. So what it means that the bifurcation parameter, which is field, changes from negative to positive. Then the S equals to 0 changes stability from stable to unstable. So corresponding to unstable, negative unstable equilibrium becoming positive and locally stable. Now, but we have a backward bifurcation when A is greater than 0 and B is greater than 0. So what it means that the S naught is, which you say that is locally stable, there exists another positive unstable equilibrium when that bifurcation parameter is between 1. So we mean that S naught become unstable and there exists a negative and local asymptotically stable equilibrium state. So we are going to see how this is applied when we make a use of examples. The next slide. Now we want to look at local bifurcations. What we mean by local bifurcation is that we want to look at the transcritical bifurcation, we want to look at saddle node bifurcation, we want to look at pitchfork bifurcations. Now let's consider we have a system of equation which is used to model a disease. This is used to model a limited treatment resources. So the details of this model formulation can be found in reference 9. So if we have a system given as equation 8 and where our treatment is given as equation 9, with K equals to R, I initial condition. So we are going to have, we are wanting to see what kind of behavior, what kind of application does this system behave. So we are going to look at how to apply that in this disease modeling. The next slide. So all the solution of this system initiated in R2, real part of this is given as it because it's divided into two populations. That is why we have our real part getting to 2. And because we are dealing with human population, that is why we have a subscript plus. So it's uniformly bounded in the region. Now the proof of this can be found in the paper cited in 9. Now if we are using T, the treatment function to be out times the infected compartment. So in the analysis of the paper, the disease-free equilibrium is given at E1, which is equal to S1, 0, and the endemic equilibrium is given at E2, is equal to S2, I2, because disease-free means that the I compartment, the infected compartment, is equal to 0. So the S1 is given at this and the S2 is given at this. Why the I is the solution of equation 11. Sometimes when you are finding the endemic equilibrium, you may end up having a quadratic equation. You may end up having a polynomial that can be of order 3 or order 4, depending. So this is the situation we have here. We do not have exact value for I2, but it has to be the solution of equation 11. So where A is given as this, B is given as this, and C is given as this. With our reproduction number given as this, of course, we have a method of deriving the reproduction number. So that can also find the derivation of this reproduction number can find in that paper. The detailed derivation can be found in the paper cited in 9. The next slide. So we say that this system 8, which at disease-free equilibrium with parameter beta star, has no saddle node bifurcation, has no pitchfork bifurcation, but it has a transcritical bifurcation. So this is what the theory is. So we are going to show how this theory is established in the next slide. The next slide. So how do we do that? Now we find the Jacobian matrix of that particular system. So this is Jacobian matrix for any equilibrium state given as equations equation 14, which you take a derivative in respect to each of the state variables. Because it's a two equation, is a system of a two equation. That is why we have a 2 by 2 Jacobian matrix. So at this free equilibrium, we have equation 15, which the eigenvalues will give us mu1 equals to lambda 1 equals to minus mu, while the second one will give us this. But the second one can be produced in terms of reproduction number, which can express as what we have in the last equation there. So the eigenvalues, lambda 2 now become what we have outside brackets, reproduction number minus 1. The next slide. The next slide. Are you there? So now, it's always good to write a disease model. It's always good to see how you can write your eigenvalues. One of the eigenvalues will actually be in terms of reproduction number, because it helps us to determine the local stability of disease-free equilibrium. So now at R not equals to 1, if we make R not equals to 1 in that previous slide, you will see that one of the reproduction number will become 0, which will be in direction of I, it will be in I direction. So meaning that it's only lambda 1 that is negative. So that means that we have two eigenvalues at R not equals to 1, where 1 is negative, 1 is equals to 0 simple. 0 simple means that there is no eigenvalue equals to 0 twice or thrice. Like sometimes when you get eigenvalue that, you have something that eigenvalue is equals to minus mu like 2 times. But this is what you mean by simple, just only once. You can have it only one. Now, how do you choose your bifurcation parameter? We choose our bifurcation parameter because we say R naught is equals to beta S1 over mu plus alpha plus gamma plus R. No, so at R naught equals to 1, we not make beta the subject of the formula. That particular beta will make subject of the formula at R naught equals to 1. We are not choosing it as our bifurcation parameter. Now, the question is that, how do you know that you choose beta as bifurcation parameters? There is no particular rule of choosing whatever parameter to be a bifurcation parameter. So it depends. So now, what the next thing we'll do now, we'll find the left eigenvalues. The left eigenvalues mean that this is equation 16. I'm going to find the eigenvector of equation 16, which is basic in linear algebra. So we multiply Z2, Z equals to Z1, Z2, B, which is when you do this, because there is 0, 0 down, we are going to get the first one is going to lead us to two equations. The first one will be that. The first one is going to give us minus mu Z1. The second one is going to give us 0Z1 plus 0Z2. Now, because there is 0 besides Z2, it means that Z2 cannot be equals to 0. So if Z2 cannot be equals to Z2 can be anything, then where our Q is generated from the coefficient that will come up from the Z1. So we have our Z given as QZ2, then Z2, where Q is given as what we have there. The next slide. So as we have determined the left eigenvalue, we are going to determine the right eigenvector. The right eigenvector has to do with taking the transpose of that Jacobian matrix at R not equals to 1. Then you now multiply it. When you multiply it, we are going to have minus mu1 equals to 0. Then the next one will give us this from what we have here now. So if for the first one, minus mu1 is equals to 0, mean that mu minus mu is not equals to 0, meaning that mu1 is equals to 0. So if mu1 is equals to 0, it means that we have a mu2, which can be any value. So mu1 is equals to 0. So we have the right eigenvector giving us this. Now we're not going to rewrite that particular model into a vector form. So the S dt equals to f of the S, where our S now become S comma I, that is the state variable of the state variable of the subpopulation of the model. Now our F now become F1, F2. F1 is the first one, the first equation. The F2 is the right hand side of the second equation. Now we'll now try to use those Sotomayor criteria. So what if first of all find the F subscript beta. F subscript beta, what it means that beta is not chosen as a bifurcation parameter. So I'm going to take the derivative of each of these F in respect to beta. So because the first F is a minus S, the first F will have a minus Si, the second one is minus, we're going to, when you take the derivative as beta, we are going to have minus Si because there is beta beside Si, and there is beta beside Si in the second equation. It gives us this. Now at disease-free equilibrium, it becomes 0 because I is 0, I is 0. So we are going to have this first derivative, partial derivative of F with respect to beta to give us 0, 0 vector. The next one. So since it gave us 0, vector, because in the saddle node bifurcation, we say that that first equation is not going to be equals to 0. Now, because it's already equals to 0, it cannot satisfy the saddle node bifurcation at this free equilibrium. So what we are going to do now is that cannot obey the saddle node bifurcation. So we are going to check other bifurcations, whether it's satisfied, because there's other bifurcation have that this first condition is equals to 0. Now, since it gives that, we are going to now find the derivative of that particular will generate the last other one. But you are not going to, the derivative means that you are not going to substitute the beta, at the disease free equivalent, you have done the derivative. So we'll now take the derivative of that f beta. When you take the first one in respect to s, you have only minus I. When you take the other one in respect to this one, you have minus s, but it's a disease free equivalent. So disease free equivalent have s1. So when you take the second one, you have at this. So at this free equivalent, we have 0, 0. 0 minus s1, you have 0 s1. So the next thing we do is that we now multiply by the left and right eigenvector. So when you multiply, for you to carry out this multiplication, which I also put it this way, this first one we have 0 w2, which has to do with w transpose. Then the second one, this is the matrix. We have the 2 by 2 matrix, which I already generated the previous equation. They multiply by our z, which is say is qz2 is qz1. When you multiply this, we'll have this. It's not going to give us, when you multiply the one inside the square bracket, it will give you this vector. You have minus s1z2, s1z2. Now when you now multiply it with the vector w transpose, is give you this, which is also not equals to 0. The next slide. Now, since it's not equals to 0, the first one is equals to 0. Since it's not equals to 0, we are not going to determine the third condition. What does the third condition say? The third condition said that we should find this square of f. Now, this square of f is not f subscript parameter, bifurcation parameter. It's the original f of the right hand side. So what does it do? We are going to generate, like when I describe the Hassan of a vector field, this is how the approach is used. We are going to determine a vector which is the vector of a matrix, vector of matrix. So this square f1 is f is a matrix of its own. For each of them, that's the equation on the right hand side. Each of them, this and this. So when you take that, it will give you this matrix. Now you now look for the second one. When you take that, it's going to give you this matrix. So by what it means that I'm going to carry each of these matrices now and put into this. So it now becomes a vector of 2 matrices. The next slide. So this is what is going to, so it's doing a vector of 2 matrices. Now we now carry out this particular multiplication. This square times s comma z, that is vector multiplied by vector. What it gives is z transpose times each of those matrices and the other z. The same thing goes. So what it means, I carry the z, I carry the substitution I got from the z, this square f1, I put it and multiply it. So when you multiply this, by the time, remember that z is equal to qz2 and z2. When you multiply this first one, it's going to give you this. This is what we are going to get, minus 2 beta star qz2 square. Remember that z1 is now equals to qz2. Now, you are doing all this at beta equals to beta star. So when you have gotten this other one, then you can now multiply with the vector w transpose. When you multiply with w transpose, you are going to get this. When you multiply, is not equals to 0. You're going to give you minus 2q beta star w2 z2 square. This is what we are going to get. The next slide. Now, by this condition, you can now see that this condition, the first one is equals to 0. The second one is not equals to 0. The third one is not equals to 0. So this satisfies the transcritical bifurcation. It satisfies the transcritical bifurcation because what it means that you have these are the conditions. So it satisfies, but it does not satisfy the pinch-fork bifurcation because the second derivative it did is not equals to 0. Is when it's equals to 0, it satisfies the pinch-fork bifurcation. So this shows us the transcritical condition. So it depends. So in a system of equation at disease-free equilibrium, it can have one bifurcation existing. You can have two bifurcations. It depends the condition is satisfied for you to have the one that that the kind of bifurcation that exists in that particular system. But remember, this is for a disease-free equilibrium. So we're going to also check at endemic equilibrium. What kind of bifurcation do we have? The next slide. Now, the same model, we want to check at endemic equilibrium that will say that alpha equals to alpha naught is equals to this, equation 17. We now say where alpha naught is positive, provided that the conditions satisfy this. So we have a saddle node bifurcation, no pinch point bifurcation, no transcritical bifurcation. So we're going to show how this is derived. The next slide. So it's the same method, the same approach we have used, but now we are using it for endemic situation. So we say that, so what you do here is that you now find the eigenvalue of endemic equilibrium. Now, but sometimes find the local stability of Jacobian matrix of endemic equilibrium, local stability is sometimes it's very difficult, especially when the system is large, when the model is complex. But we are doing that because we have a 2x2 matrix. We have a two system of equation. So we choose a bifurcation as this. How do we choose this bifurcation? Now look at your Jacobian matrix, not as eigenvalue equals to 0. So look at Jacobian matrix. We have this Jacobian matrix, I think not at eigenvalue equals to 0. It's supposed to be generally the Jacobian matrix of E2 is a mistake with this lambda bar equals to 0. It's supposed to be E subscript 2. So when we choose this, when you take the eigenvalue of this, you end up having eigenvalue that will give you something that will lead to this. And so by having that, from that, so you now choose a bifurcation where one of the eigenvalues is equals to the, that's how you choose your bifurcation parameter. You are choosing your bifurcation parameter where one of the eigenvalue will lead to 0. That is how to choose the bifurcation parameter. So that is how we make the choice of alpha equals to alpha 0. Just like the way we did for disease-free, for this particular one now, you choose it in a way that's where one of the eigenvalues is equals to 0, why the other one be negative. So when you expand this Jacobian matrix here, you're going to lead to where this alpha naught is equals to this. That will lead us to having it equals to 0. Now, the next approach we do is the same approach we use. You have to choose your left eigenvector. We use the left eigenvector. This is what we have. The next slide. We'll multiply it, then we'll lead us to what we have in the next slide. The next one. So we now have this system. This is equals to this. This is equals to this. So when you solve this simultaneously, you know that eigenvectors, it doesn't solve like the way you solve this equation, simultaneous equation. There's a way we solve eigenvector. That basic is in linear algebra. So when you solve this, you are going to have I2, L2, and your L1 to be equals to L2, which Z2 is given as what we have as this. Now you also have to find the right eigenvector by transposing that particular matrix. When you transpose that particular matrix, you now multiply it with another eigenvector, which you call H. We're not going to give us it. When you now do the same equation as we expand it, you are going to have H equals to Q, H2, and H2, meaning that H1 is equals to QH2, and where the Q is given as this. The next slide. So we now compute. Of course, you are going to write your system as what we have dy dt, where the left hand side becomes. We are using y because I've used s for disease. We are using y, but still the same model we are using. So when you do this, you are going to take the partial derivative of it to produce your f alpha. Now we are using f alpha because alpha is the parameter that is the bifurcation parameter in this case. The previous one was a beta that is a bifurcation parameter, but now it's alpha that is a bifurcation parameter. So we are choosing this, and when you do this, this is what we have our f subscript alpha. And when you do this, you are going to have 0, I2, because our I is not this I is supposed to be this one's supposed to be a positive. This minus supposed to be a positive. Please, is a error. So you're going to have your f subscript alpha to be 0, I2. Now in see when you multiply it, it's not going to give you it's no longer going to give you 0. It's going to give you something. Now because it will not give you 0, now we'll not carry out the next condition, because once it's equals to 0, that means they are going to be reading as, oh, am I going to have a transcritical bifurcation, am I going to have a pitchfork bifurcation? But once it's not equals to 0, it means that you're going to really need to saddle node, but you have to check other conditions. So the next thing we are going to do is that we carry out this second derivative multiplication, which we have showed details how to do it. You now produce your get your d square. D square is gotten as what you have as beta 2 by 2 matrix, which I showed you how to get it in the previous one. When you multiply this, it's going to give you this. The next slide. So with this multiplication, we now multiply, we now see that this is what we have is not equals to 0. And since it's not equals to 0, by Sotomayor's theory, we see that transcritical and pitchfork bifurcation does not exist. But by the condition of saddle node bifurcation, we see that it exists because it's not equals to 0. So it means that that system has a saddle node bifurcation at near endemic equilibrium, while it has a transcritical bifurcation near disease-free equilibrium. So that is what that particular model. So what you see that now is that it will help us to determine the kind of bifurcation this system has. So the next thing we do now is that we also try to look at other bifurcation, mostly the forward and backward bifurcations, which is most largely used in disease modeling. The next slide. Now, for the forward and backward bifurcation, we're going to give many examples, but it depends on the time. So we consider this system, which, of course, the details of this model formulation can be found in reference 1. And the model is proposed in reference 1, but the details are found in the reference 8. So what we have here is that, of course, S is a susceptible class, B is vaccinated, and infected is I. So for the formulation, we can find it in equation model 1. Reference 1, the next slide. The next slide. Okay, so the first of all, because you cannot do if you don't actually know your equilibrium state and the stability of it. So from the paper, they already established the disease-free equilibrium, which is E naught given as this, and the arrow naught given as this. Then the endemic equilibrium is established as this, where I is the real positive solution of the equation. So the I is the equation of this 19. Now most times the bifurcations, as I said before, sometimes the endemic can lead to a quadratic equation, a polynomial of any different degree. So this is what we have. And when you're having something like this, it's always good to see how your coefficients can be written in terms of reproduction number. So this is what we have as our A1, A2, A, and C. And it helps you to analyze the condition of this equation 19. The next slide. So from that A1, A2, A3, of course, if you look at A1 is in the previous slide is always negative because there is a minus sign. Now, but C, your C depends what is the behavior of a reproduction number. If it's greater than 0, if it's less than 0, it depends on the behavior of the reproduction number. But your B, we don't know exactly what is B because you cannot say that B is positive or negative because you also do not have the values of those parameters. So therefore, we establish a table. This table is based using a sign, and that just using a particular sign. What this sign says that you have to look at the signs of each of these coefficients. Now, if the sign of A is negative, the sign of B is negative. That is the case 1. And sign of C is positive. Sign of C can be positive if our reproduction number is greater than 1. Now, what do we mean? So you now look at what is the change of sign. If you look at the change of from negative to negative, the sign will not change. But from negative to positive, that's from B to C in the first case, the sign change. How many times do this say 1? It means there's a 1 possibility of real roots, that positive roots. That's why we have 1 in the last column there in the line. So, and that happens when the portion number is greater than 1. Now, the second one, you now look at if B is, because we say that A is all true negative. So if B is positive and C is positive, the sign do not change. It's only one sign that changed, meaning that we have one endemic equilibrium. Now, the second one, if B positive and C is negative, and C become negative if the reproduction number is less than 1, the sign changed twice. It means there is a possibility of 2 endemic equilibrium. Now, with 2 endemic equilibrium existing when reproduction number is less than 1. Now the next one, when B is negative, everything there is no change of sign. That means there is no change of that, meaning that there is no endemic equilibrium existing. Now the condition 3, the case 3, is there is a possibility of backward bifurcation scenario because R naught is actually less than 1 and there is existence of endemic equilibrium in that the third one. And then also, when the discriminant is equals to Z, discriminant, like what we know in quadratic equation, the discriminant is under the square root, which is given at B squared minus 4AC. When is equals to 0, there's also a critical point you can establish there, which will give you a saddle node bifurcation, making appearance or loss of 2 positive endemic equilibrium in a backward bifurcation framework. Now, when you have this condition, it's always good to go further to determine the whether you actually have a backward bifurcation. But from the case 3, there's a tendency of backward bifurcation because reproduction number is less than 1, and there's a existence of endemic equilibrium, which is 2 endemic equilibrium. So which you can further establish using the center manifold theory. The next slide. Then so what do we do here? What we do here for you to establish to use that condition? So this is the Jacobian matrix of local stability as this. Of course, the eigenvalue can be done by
Sorry, Dr. Chinwendu, I think we lost you again. Dr. Chinwendu.
especially
All right.
in the sense that when you look at a row or column in that, the eigenvalue become that second column. Is it you can determine this eigenvalue without solving them? You can do them by expression. Maybe we can also look at by expression in the sense that for the second column of this matrix of the equation 20, the only parameter in that second column is minus mu, and it's a diagonal element. So the eigenvalue in that particular become minus mu. You cannot eliminate the second column and the second row. Then you can find the other one. So it find the eigenvalue becomes easy of solving the eigenvalue as a quadratic equation. So we have the eigenvalue 1 given as this, eigenvalue lambda 2 given as this, lambda 3 is given as this. Now the lambda 3 is given as this, which can make it to be in terms of reproduction number, as I said before. Now we now see that the reproduction number, all the eigenvalues are negative if reproduction number is less than 1. All the eigenvalues, 1 is positive and others are negative if the reproduction number is greater than 1, meaning that it's unstable. It becomes unstable equilibrium. So now for this particular one, since all the eigenvalues are negative, except this lambda 3, which has to be in the condition of reproduction number, we cannot determine our bifurcation parameter when R0 is equals to 1. So if R0 equals to 1 here, we cannot choose our bifurcation parameter because if it's equals to 1, the eigenvalue 3 becomes 0. Because we say that we can actually determine this when eigenvalue is equals to 0. Simple. Others are negative. The next slide. So we now observe at R0 equals to 1, C is equals to C star. We choose C as a bifurcation parameter. The reason why we choose C as bifurcation parameter because beta is not common in all of them. Beta 1, beta 2. But sometimes beta can be chosen by making beta 2 be in terms of beta 1. So it depends. That's why I say the choice of your bifurcation parameter also depends on you. Although there are no particular method of that in my own knowledge. So now we will now see that there's a loss of there's a transcritical bifurcation. Now I want to let you know that there's a relationship between transcritical bifurcation and forward and backward bifurcation. We are going to see that. So transcritical bifurcation, when you have existence of transcritical bifurcation, if you go further to examine the backward and forward bifurcation, it can actually establish them in that transcritical bifurcation. One will give you a transcritical bifurcation, supercritical transcritical bifurcation. One will give you a subcritical transcritical bifurcation. So there is a relationship between both of them. Now we look at the backward bifurcation. Actually, I'm not supposed to say, okay, we have a backward bifurcation. Is it the last end of my result will determine whether it's a backward or forward bifurcation. Now, applying the center manifold theory, we have as C equals to C star now. That's at R0 equals to 1. And I've replaced that last column in terms of alpha plus mu R0 because I have established my eigenvalue 3 to be in terms of that. So I now have lambda 1 equals to this, lambda 2 equals to, and lambda 3 equals to 0. at R naught equals to 1. The next slide. Now, when I do that, of course, we will do the left eigenvector. The left eigenvector, the way we did it in the former bifurcation. When we do that, we solve it. We are going to have this eigenvector, this right eigenvector, which is given as this. Now, we now establish the left eigenvector. The left eigenvector is established by making, like this particular eigenvector, equation 21, is established by solving that Jacobian matrix with W. W is giving omega 1, omega 2, omega 3, because it's 3 by 3 system of equation. When you solve it, you are going to get this equation 21. Now, for you to solve the left eigenvector, you are going to take the transpose of that particular matrix, previous matrix, at R naught equals to 1, the critical. You are going to take a transpose and multiply it by V. When you multiply it by V, you are going to get this equation that you have, this last equation. Of course, if you look at this last equation, you can see that V2 is going to give you 0. Before you can now say, okay, V1, if V2 gives you 0, because minus V2 mu is equals to 0, mu is not equals to 0, mean that V2 should be equals to 0. Then when you give you 0, you now see that V1 will give you 0. If V2 gives you 0, in the first equation, V1 is going to give you 0. Of course, you are going to get V3. So V3 is no longer going to give you 0. So we now have, because V3, by the time you have V1, V2 equals to 0, you now see that V3 here, which is alpha plus mu, R naught minus 1, V3. So if R naught is equals to 1, it becomes 0. It means that V3 is multiplied by 0. So 0 multiplied by a variable, means that that particular variable is not equals to 0 because there's already 0 attached to it. So the next slide. So the next slide, we are going to have our V to give us 0, 0, V3, because we said V1 is 0, V2 is 0. So we have this. Now, in this, both left and right eigenvector satisfy the condition that the vector V and vector W multiplied together is equals to 1. And each of these vectors is multiplied by each of its corresponding component, V1 W, V1 W omega 1, multiply like that. So since V1, V2 is equals to 0, so you have that, okay, V3 omega 3 is equals to 1. Now, the next thing you do is that you take the second partial derivative of non-zero component of left eigenvector. Now, instead of you to come and be taking all the second partial derivative of everything, it's always advised, okay, when you see that particular V that is not equals to 0, which is V3, they mean that I should go to the third equation, right hand side, which is become my F3. I will not take the second partial derivative of it at the critical point at disease free equilibrium. Remember that disease free equilibrium, this is what it is. So if I take the derivative in respect to S2, I'm going to get 0. In respect to V, S2, I'm going to, so at the end of the day, this is what the second derivative will give me in that particular third equation. I do not consider the first and second equation because my V1, V2 is equals to 0. That is one that will consign those equations. So because it concerns only V3, that is why I take only the third equation. The next slide. So in the next slide, so we now determine the A and B. How do I determine the A and B? Remember, so because the A and B are in terms of Sj, so you are going to transform your state variables into the so my S become my S1, my V become my S2, my I become my S3. So this, the A1, I'm going to do this, expand it. So in the expansion, because my V1, V2 are all equals to 0, I do not care about the V1, V2 components. We're only concerned with V3. But when in a situation where it's not equals to 0, you're meant to put everything out. And sometimes even when the second derivative are equals to 0, you are not so, possibly you can also leave those one that is equals to 0 to in form of your multiplication, in form of your expansion. So in this case now, my second derivative is S2. Now, because remember my S is S1, so the second derivative is that means I'm having S1. So my W is one that has to do with S1, S2, S3. So that is why my W1, my omega 1 is square here, because it's S1 square. The same thing goes with S. So that is how I got this expansion of A. Now for B, this is how I got, the B has to do with the critical points, that bifurcation parameter. So I'm taking each of those state variable. The second derivative will not be the state variable and the bifurcation parameter. So my omega 1 will not determine the state variables. My bifurcation parameter is there. This is how this A and B are expanded. The next slide. Oh, Is that the next slide? Okay, the next slide now, this is what we have. By the time you substitute everything, your W and V, the W that is in equation 21 and your V that is 0, V that, when you multiply, this is what you are going to get. You are going to get it, but your A naught is equals to, what is happening? Okay, your A naught is equals to this expression that is given here. Now, this expression, it's possible for you to say, oh, A is less than 1, less than 0. But you cannot establish that A is less than 0 because there is A naught in which there is a negative inside the A naught. So it's only in the numerical simulation it can establish that condition, whether it's a forward or backward bifurcation. So in this case now, our condition of forward or backward bifurcation depends in the sign of A. If my A is negative, less than 0, because of course B is positive in this case. If my A is less than 0, it means I have a forward bifurcation. But if my A is greater than 0, it means I have a backward bifurcation. So the sign of my bifurcation now depends in the sign of A. So therefore, I have a forward bifurcation if A is greater than 0. I have a backward bifurcation if A is less than 0, and which also depends on A naught. So that is the condition that leads to whether it's a forward or backward bifurcation. So that is for this particular model now. We have a forward bifurcation if A is less than 0. We have a backward bifurcation if A is greater than 0. So how do you establish that? You are not going to carry a numerical simulation by getting the parameter values of this. When you explore the parameter values, remember, they say the bifurcation happens with the change of parameters. So within your parameters now, if you look at this parameter A naught, if you choose your parameter in the sense your A naught are positive, it means that you have a forward bifurcation that is to show. If you choose your parameter in the sense that A naught is negative, it means that you're going to have a backward bifurcation. The next slide. So the next thing will show the next example too. Which the next example is the same approach. It's not going to be far from what today, but this is is a more equation. Equation 23. We have this. This was used for a dengue fever, which has to do with a couple vector dynamics. So we have the model. The details of this formulation we can find in reference 4. The next slide. So of course, in the paper, it had already established the disease-free group up. It's already established the local stability. They already established the reproduction number. They already established the endemic K group up, which leads to the quadratic equation we have in equation 25. The same approach that we have used is going to be carried out. The next slide. The same approach we have used in previous one is going to be carried out. So I think we can. The next slide. The next slide. So the same table, the same condition of the table. This table is always very important because it helps you to know where you are having possibility of a backward bifurcation. So the same explanation I gave in the previous the same explanation that is going to condition here too. If you look at here, A is always positive in this case, but B is the one you don't know whether it's positive or negative. And your C, also the positivity, whether it's positive or negative, depends on the condition of a reproduction number, whether it's greater than or less than. The next slide. So from that particular model, they established that the reproduction number has only one endemic K group. Of course, you have one endemic K group if R0 is greater than 1, which you can find by solving the quadratic equation, like this equation, the proof. By using a quadratic, you give you an endemic equilibrium. But there is a possibility of 2 equilibrium states, which it can also happen when the reproduction number is less than 1. So it now may lead to a backward bifurcation, which you are going to establish by using center manifold theory. The next slide. And for backward bifurcation is what we call subcritical transcritical bifurcation. The same approach you are going to use, but this what we have here is 8 equations. So which is we have already established in equation 26. Each of them will call F1 to F8. The next slide. Then you have you establish your local stability of the eigenvalues of the Jacobian matrix, which you can done by inspection. But establish 8 by 8 local stability of eigenvalue of 8 by 8 matrix sometimes can be very complex. You can do that by inspection, By that inspection, you can get all the eigenvalues without going to solve all of them by inspection, looking at it using the condition of linear algebra, background of linear algebra. I can get the eigenvalues of this Jacobian matrix 8 by 8. The next slide. So we established of course, the left eigenvalue and right eigenvalue is going to be of dimension 8 because it's 8 equations. We have it established this. They also established your W, you establish your V. The next slide.
Sorry, Dr. Chinwendu, you only have 10 minutes left. Is that okay?
It's not okay, but I will try.
Okay,
Okay,
thank you.
I'm going to skip this. Okay, you now establish
All
your
right,
A.
okay.
You are going to get the second derivative because we are like what I said before. You focus on the V components that you have. So we have V2, we have V5, we have V8. So we now take the components. Now, because is a mixed partial derivative. So we take the mixed, when you take the mixed partial derivative, it can lead it because if you take respect to S1, respect to S8, they are going to give you sentence respect to S8, respect to S1. So this is what you have in equation 28. Now you now compute your A. You have the A given as expression in equation 29. Now you now get your A, expand your A in equation 30. You have what you have in equation 30. The next slide. So we now have your A. Continue. So A will now lead you to equation 31. When you expand and simplify, you get equation 31. Now you now go to B because B has to do with a beta. You are choosing your beta as a bifurcation parameter. Oh, I forgot to say, choose your beta as a bifurcation parameter based on your eigenvalue that leads to 0. So you now have equation 32. Equation 32 is what you have here. You take a second derivative. You have equation 32. Then you now substitute those derivatives to give you, this is what you have. V8, W8 give you which is greater than 0 because these other components of second derivatives for based in beta for F5 and for F5 because there's no beta in F5 components. That's why it's equals to 0. The next slide. So we now have this condition. Your A, so somebody said I'm talking too fast. Sorry. I'm sorry for talking too fast. Okay. Then your B is always greater than 0. But the sign of the kind of bifurcation you have depends on A. So you have it that your A is less than 0. If only if this alpha is less than, this phi is less than this. Your A is greater than 0. If only this psi is greater than 0. So that is what that leads to this. Now, I also want to tell you there's a relationship between transcritical bifurcation and forward bifurcation. When you have a subcritical transcritical bifurcation, it gives you a forward bifurcation. Same thing as forward bifurcation. When you have a supercritical transcritical bifurcation, it gives you a forward bifurcation. That is what this last observation means. The next slide. So there is another example, but this example I'm not going to solve further. This is another example you can also try on your own. Of course, to lead you to what you have. This is a model you have. Details in the equation. You follow the same approach. The next slide. So the next slide, you now have this is a condition based in that table. If you use that particular table I've given the example, the previous example, you will establish these conditions. But sometimes, because there's a possibility of backward bifurcation, so it's always good, if possible, to solve it, or it can numerically show it by example. Oh, this is the way the backward bifurcation. Then the backward bifurcation can actually be shown by that quadratic equation. The next slide. So this is another example. So now, there's a common causes of bifurcations in disease. One of those common causes of bifurcation is reinfection. Reinfection most times cause a backward bifurcations. Also, sometimes vaccination also cause that the partial worming. When vaccination is not 100%, of course, you can't have 100% vaccination. It can also cause backward bifurcations. So this is an example of a model. The details are fine. Reference 1. It shows a backward bifurcation. Now remember, You can actually have a forward bifurcation when that particular parameter that causes it is equals to 0. And when that parameter is equals to 0, there is a tendency that you can have your global stability of each of the endemic equilibrium that you have. So that is what the theory said. When there is no reinfection, the global stability, the disease spread is globally stable if the reproduction number is less than. So this reproduction number is already established in the paper. The next slide. Now, other causes of it, of course, I would say imperfect vaccination, reinfection, have a multiple groups population, like you are modeling men, women, children, you are considering them what maybe different subgroup in a model. Treatment can also cause that. Resistance to treatment mechanism can also cause that. The structured acquired immunity can also cause a backward bifurcation. These are these things. You can find this example in reference 1. Some of these models in reference 1, which can also check in details the behavior of the bifurcation. The next slide. So now, the reason why I put this is that this is one of the papers I use in a monkeypox model. Monkeypox, one of my paper in reference 2. So we established a backward bifurcation. If you look at that paper, this equation 35 is there, and which leads to what you have here. This is a polynomial of degree 3. So when we use a code, a bifurcation code. The bifurcation code, which I can also send, if you want the bifurcation code, I can send it in request. So what the bifurcation does is that bifurcation code, there are so many methods you can use. There's a math count in a MATLAB you can use to do bifurcation, any type of bifurcation. But I use this particular code for my backward and forward bifurcation. So what this one does is that within this code, you slot in this polynomial. When you slot in this polynomial, you put everything, then you run the simulation. It will give you what we have in the next slide. The next slide. So it will give you what we have in the next slide. So this is what is generated from that equation 35. So the red one is endemic equilibrium. I told you that when you have a backward from what we established from the table, you can have a possibility of 2 endemic equilibrium existing. So if you look at this case, there are 2 endemic equilibrium existing in reproduction number less than 1. Now, this is reproduction number. The reproduction number we have here is a subscript 0R because in monkeypox, we have rodents, we have a human population. So this has to do with reproduction numbers of the rodents. So the blue one is a disease-free. Of course, is 0. A disease-free, that means if infected is 0. Giving this force of infection to be 0 because force of infection is a function of infected population. So we now have it 0, mean a local stability. But within the same, it's not up to 1. You have a slight curve black, which is endemic equilibrium, which is a small endemic equilibrium situation within this reproduction number. Then there is a bigger endemic equilibrium, which is the red one. So this is the example of a backward bifurcation. This is generated with the previous slide, which I can also give the code. Anyone that requests for it. I can also do the explanation to anyone that wants to use it. So that is all for today. Thank you very much for the opportunity to present this presentation. Backward bifurcation is an opportunity to present this to the institution. I am very grateful and I'm open for questions. Any questions students can ask me, anybody can ask me. I'm always free to explain to anybody. Thank you very
All
much.
right. Okay. Thank you very much, Dr. Matubuizi, for the very insightful and inspiring presentation. And we will now move to the question and answer session. Participant, please raise your hand or write your question in the chat box, and I will start by reading 1 or 2 questions from the chat. Is there anyone want to ask Dr. Matubuizi live? No one? Okay, maybe I will start first, Dr. Matubuizi. It's just a silly question, but it's quite uh, interesting. Dr. Matubuizi, in a simple epidemiological model, it's quite easier, right, to determine the basic reproduction number R0 as a threshold parameter. And when the R0 is equal to 1, then we will have the transcritical bifurcation, right? So I just wonder, for example, if we have more complicated model, So it's not really easy to find out about the Arnold. So I just wonder, is it still possible to identify or analyze the bifurcation behavior, and how would we approach it mathematically, and which parameter is more interesting to the bifurcation analysis in epidemiological model? Dr. Madubuisi, thank you.
Okay, thank you very much. Sometimes you may have a complex model in which the reproduction number is very difficult to establish by using the next generation method. Using next generation method. But there are other methods you can actually use to compute your reproduction number. You can use the local stability of disease-free equilibrium, the constant term. When you have the polynomial, the constant term can actually can help you to establish the reproduction number in that case. Now, bifurcation parameter, there's no particular parameter that you say, okay, this is what I will lead you to bifurcation parameter. But in the course of teaching, the bifurcation happens when one eigenvalue is equals to 0. So now, if I don't establish the eigenvalues of a Jacobian matrix, I will not know.
I think we lost you again, Dr. Madubuisi. Hello, Doctor. All right, okay. I think we lost at the moment. So yeah, maybe I have to say sorry for all the participants for this inconvenience, some delay. Dr. Chinwendu. Hello, Dr. Chinwendu.
I think, yeah, connection issue ya.
Iya, Bu.
Ya. Diulangi lagi aja, Pak Rudin.
Yeah, right. Okay. Dr. Chinwendu, are you still there? Hello, Dr. Chinwendu. Yeah, I'm really sorry for all the participants for this inconvenience internet issue. I think we lost Dr. Chinwendu now. Let's go.
Ya, kayaknya terlempar ya.
Iya, Prof. Ya, mungkin Bapak Ibu mau
Ya,
menyampaikan.
ditunggu aja ya.
Ya.
Tadi udah nyampaikan. Saya chat beliaunya. Itu
Ya,
ada
Bu.
di chat roomnya juga ada pertanyaan nanti.
Ada dari Pak Dipo. Ya, nanti setelah beliau kembali akan
saya
tanyakan.
Alhamdulillah. Morning, ma. Yes.
masih saya cek juga, itu kok centang satu masih. Ya, sana katanya listriknya sih bermasalah juga, apa ya?
I'm sorry. It seems
All
like
right,
it's my
okay.
network.
Okay.
All right.
I'm sorry,
Welcome
it's network.
back.
It's network, I'm sorry.
Yeah, it's okay. Thank you so much, Dr. Chimendu. So we try to answer the last question, right? You mentioned about the eigenvalue for some parameter. If we have Arnold, it's not easy. I mean, for complicated model, for example, like if we consider about the seasonal fluctuation, so it's not easy to find the Arnold, but we still okay with the next generation metric, and then we consider about the eigenvalue. So you can continue your explanation for the last question, Dr. Chinwendu.
Okay. Yeah, okay. What I was trying to say is that Sometimes, like for example, I have some paper that I did Lassa fever. Sometimes
Okay.
the production number is difficult to get using next generation method, but there are other methods you can use to establish the reproduction number. One of them is establishing your endemic equilibrium. In the condition where your endemic equilibrium is positive, that condition can be taken to be your threshold quantity, because reproduction number is a threshold quantity that establish the condition of disease elimination or persistence. Now, you can also use the local stability of disease-free equilibrium. The local stability of disease equilibrium, when you solve it and have your polymonia, the constant term, the constant term is where you can make it. If you watch in the presentation, the constant term is where we establish R not equals to 1, making the eigenvalue to equals to 0. So in that constant term, where you have put the constant term, that's condition that you have something is less than 1. That condition, that item that is less than 1 can be established to be your reproduction number. It can be established to be your reproduction number. You understand? So the production number can be established using the local stability. Now, in the case of that is not possible, you can use the numerical simulations. But in using the numerical simulations, in determining which of the parameter causes that bifurcation, first of all, you have to plot your graph. Then you can use this MATLAB MATCOMT is a particular this in MATLAB, which they use for bifurcations. In that case, it can test the parameters, and which can be very, very cumbersome. And that is why quantitative analysis become very important, because it helps you to identify which parameter to focus on. But in numerical simulation, you are carrying out the simulation. So it means like you have to keep on detecting which of the parameter that will cause a behavior in the system by numerical simulations.
All right. Okay. Yeah. All right. Okay. Thank you so much, Dr. Matubuisi. We have one question in the chat box. Or Pak Dipo, do you want to ask Dr. Matubuisi live, or should I just read your question, Pak Dipo? Okay, maybe I just read the question from Mr. Dipo. In slide number 47, you mentioned that your model always has two endemic equilibrium for R0 less than 1. And the question is it always true for all R0 less than 1 and for any parameter value chosen from the model? If yes, then we have interesting discussion on the interpretation of the basic reproduction number. Thanks for your explanation. That's the question, Dr. Chinwendu.
Okay. I need to see slide number 1. So I'm trying to open my laptop to
Or maybe
see
we
what
can
is
open it
there.
for you. We can
Okay, you
open
can
it for
open it
you.
for me. Slide number, yes, slide 47. Thank you. Okay, this is 47. Okay, this is 47. Okay, you mentioned that your model always have two endemic equal for reproduction number. My question
The
is, you
second
always,
theorem.
yes, I know. Is it always true for, I don't know, like, for any parameter choosing from? If yes, then we'll have it. Okay, now from this particular, it must not be two endemic equilibrium. It depends the kind of model you have. Sometimes it depends that the polynomial you have in this case is a quadratic equation. It depends in polynomial you have. In the conditions of the coefficient that will determine how many endemic equilibriums you have. For this theory is made based on that particular model. In another different model, it may be another different theory that may generate from that. Now, for the choice of parameters, in bifurcation analysis, sometimes the choice of parameter values also affects the dynamics of that bifurcations. So it depends the kind of model you are studying at that particular time. Thank you very much.
All right. Okay. So we are going to the next question. This from oh, Pak Thibault want to see the model.
Okay, you said the second theory. Okay, so he wants to see the model.
Yes.
The model.
So it will be in 40. Which slide is it? Is it in 48 or 40?
I think this is supposed to be the model. So this is the model.
All right, okay. So this is the
Is
model,
a
Pak Tipo.
yes.
Yeah, maybe
Yeah. So the second theory, he mentioned about the second theory in that 47. But this is a model, is a model that has to do with human population and mosquito dengue, mosquito vector. So is a different host populations. So slide 47, he mentioned the
so is
second
that clear, Pak?
theory.
Yeah. Yeah, so this is a model, right? For the 47
Yes,
slide. So, Pak
yes.
Thibault, is that clear, or do you want to ask another question? More than one type of population? Yeah, I think so. Yeah, we
Yes, I
have.
have more than one population. Yes, I have. I have a vector and human population.
All right, so it's clear,
Okay.
Pak Thibault said. So we are going to
Okay.
the next question, Dr. Chenwendu. So we have one question from Professor Abadi. Nice and instructive presentation. Could you explain what does the meaning of the condition when R0 is less than 1? And then an endemic situation occurred. Is it possible a backward bifurcation happens simultaneously with a forward bifurcation? Thank you.
Okay.
That's the question, Dr. Chinwendu.
The first question: when R0 is less than one, an endemic equivalent, and there is the existence of endemic situation. What implies is that we have this abdomen of R0 that when it's less than one, there is a tendency that the disease will be controlled as times goes on. When it's greater than one, there is a persistence of disease in the population. Now, awareness happens at when there is no disease, but one person is introduced into the population. So, when there is a coexistence of endemic situation when R0 is less than one, what implies is that even when R0 is less than one, the disease can still persist in the population unless a further intervention is carried out. That is what it implies. And this, in the condition of endemic equivalent existing in the bifurcation where R0 is less than one, if you look at that endemic, it's very, very close to one when it happens. It's very close to unity one in the when it happens in the diagram. So the endemic situation occurring less than when R0 is less than one means that the disease will not die out as time goes on. Because if you look at the project of a disease, there it will rise and peak and start going down after a while. You're like when so there's nothing like, okay, disease continues and continues forever. At a time, the disease will die out. Now, for R0 less than one and there's endemic situation, if nothing is done at that stage, the disease will not die out as time goes on. It will continue to persist, even when the reproduction number is less than one. So other intervention has to be implemented. Now, is it possible to have a backward bifurcation simultaneously with a forward bifurcation? It depends in the conditions. It depends in the condition. A model can have backward and forward bifurcations. It can has it, but it depends in the condition, which I told you that backward and forward bifurcation has a relationship with transcritical bifurcations. So when the bifurcation parameter is passing through, changing from zero, changing from from one to another side, it means that there is a change of stability. You understand? So the backward and forward exists based in the condition of bifurcation parameter. Is it less than what it is? Is it greater than? That is what happens there. But two can exist in a model, but it has to be based on inequality signs.
Right, okay. Is that clear, Pak Abadi? Or do you want to ask another question? Uh, okay, thank you. Okay, anyone else want to ask Dr. Chinwendu directly? Just raise your hand. Maybe, okay. We still have 5 minutes left, Akbar. So you want to ask Dr. Chinwendu directly? Okay, go on. Another question, Dr. Chinwendu.
Okay.
Okay, thank you so much,
Okay.
Professor Chinwendo. So, we ever try to did analyze of bifurcation, and then the one of the most challenging is that to determine the parameter that we have to use, or the parameter that we have to choose to we analyze in bifurcation analysis. So is there any specification, or like is there any condition, or which parameters that we have to use?
Okay. So thank you very much for your question. Now, like during the presentation, I said that the method of choosing any parameter, in the best of my knowledge, I don't know the particular method, but for you to go into bifurcation parameter, one of the eigenvalue must be zero, simple. That's one of the eigenvalue will be equals to zero, simple. That is occur twice, occur only once. Now, if you now look at what is the condition that make one of the eigenvalue to be equals to zero. So in that condition that makes it to be equals to zero, any of the parameter that you can choose there, when you slot it in and it makes the particular eigenvalue to be equals to zero, can be chosen to be the bifurcation parameter, to the best of my knowledge for now. Maybe I have to read further how to choose the bifurcation parameter, but it has to come from the eigenvalue that is equals to zero. And that is why it happens, because one of the eigenvalues is established in terms of R naught minus 1. So when that R naught equals to 1, that eigenvalue becomes 0. Now, when it becomes 0, R naught equals to 1, meaning that R naught is already a term on its own. So that term that represents R naught, which are the parameter in that term of R naught that makes it to, that satisfies R naught equals to 1. Now, for the case of the endemic situation we established, we look at the bifurcation around endemic. It still boils down to Jacobian matrix. I choose my Jacobian, I find my eigenvalues. Which parameter makes one of the eigenvalues to be equals to 0? That parameter that makes one of the eigenvalues to be equals to 0 is now become what I choose as my bifurcation parameter. For now, I don't have a particular method. Maybe it's a study to consider. How can I choose bifurcation parameter? Thank you.
Thank you so much,
All right.
Doctor.
All right. Okay. So anyone else? No one? Right. Okay. I think we are going to the end of the session for this afternoon guest lecture. So I would like to say thank you to all participants for your interesting question, and to Dr. Matubuizi for the clear and thoughtful responses. Before we close today's session, we would like to express our sincere appreciation to Dr. Chinwendu Emilian Matubuizi for sharing her valuable time, knowledge, and insight with us. As a token of appreciation, allow me to present a certificate of appreciation on behalf of the FSC Erlangga University. Please, the committee. Prof. Fatmawati, do you want to speak for this one?
Yeah, thank you, Prof. Chinwendu, for your contribution to our webinar as a speaker. Thank you very much.
Thank you very much. Thank you for the certificate. I appreciate. Thank you so much for the collaboration and mentorship. I really appreciate it. Thank you so much.
Yeah. And I have one question. Could we share your slide to our participant?
Yes, I can also share the code to the last graph too.
Okay.
Should I send it to
Thank you.
or should I? How do I send it? Or should I put in my email for the slide and the code? Or then I can also share the slide and the updated slide and the code to you too, if that is okay by you.
I think I can. Yeah, we can share the slide via chat room ya, Mas Akbar. Yeah. Oke, thank you very much once again. Ya, bisa di-share aja slide-nya ya.
Oh iya, Bu.
Oke.
Iya, siap.
So let me just put I just want to input my email so that people can reach me for the slide.
Yeah. Okay, you
Especially
can
those
share your email.
Yes, especially those from Nigeria.
Okay, Harrison. Dr. Harrison on the PC. Do you have?
So this is my email address.
Oke, silahkan yang mau diskusi atau mau join research. I think Prof. Chinwendu is very welcome ya, Prof.
Can I ask a question? Can I ask a question? There's a okay, there's a link here. Fill in the attendance to. Is it for the participant or is it for everybody? The link.
Yeah. Okay.
Is it for
I think the computer, the computer will share the. I don't know.
Sorry, but I read in the chat box there is Dr. Harrison Madubuisi would like to say something. Do you want to say something, Dr. Harrison Madubuisi?
Yes, good morning.
Good morning. Yeah.
Sorry, I just joined while Dr. Emilia was talking. I'm just to say thank you to Dr. Chinwe and to appreciate the organizers of the webinar. Dr. Chinwe is my wife in my own culture. She's a wife to my elder brother. So she invited family members to join the webinar this morning. And we have to just pause whatever we are doing to witness her. And I think her children are also watching her speak. So it's a humbling moment for the family. We appreciate you people. We appreciate Dr. Chinwe. And thank you very much for the organizers. Thank you.
All right. Thank you, Dr. Harrison. So lovely.
Yeah,
right,
thank you so much.
Okay. Once again, congratulations for Dr. Madubuisi, and thank you once again for your inspiring contribution. And ladies and gentlemen, as we come to the end of today's session, let us again extend our deepest appreciation to Dr. Chinwendu Emilian Madubuisi for her outstanding lecture. And your presentation has deepened our understanding of how bifurcation theory can be applied to epidemiological model and has inspired many of us to explore this fascinating field further. I would also like to thank all participants for your active engagement and enthusiasm throughout the session. Before we officially close our session, we would like to take a group of photos together as memory of today's guest lecture. So I kindly ask everyone to please turn on your camera for a moment, please. And let's take a nice picture together. For the committee, handle the photo session, please. So open your camera. Are you ready for the committee? Okay, so for the first screen, smile everyone. Right, so we are going to the second slide. Okay, for the third one, and for the last one. Thank you so much, everyone. So with that, I now return the floor to our Master of Ceremony to official close the event. And thank you, everyone. Have a wonderful day. And wassalamualaikum warahmatullahi wabarakatuh.
Untuk slide-nya sudah saya share ya di chat room ya. Monggo Bapak Ibu bisa diunduh. Kelihatan ya.
Terima kasih, Bu.
Okay, thank you so much for the moderator, Mr. Dianto Ariano. So, very nice talking from Dr. Chinwendu Emilian Madubizi, and also very good explanation, and then reply our questions with greatly. So, ladies and gentlemen, as we come to the end of today's guest lecture on the topic application of bifurcation analysis to epidemiological models, let us express our deepest appreciation to our distinguished speaker, Dr. Chinwendu Emilian Madubizi.
Okay.
Okay. We would like also to thank Professor Dr. Fatmawati, Master of Science, and all committee members who have made this event a success. Last but not least, thank you to all participants for their attention and active participation throughout the session. We hope today's lecture enrich our understanding and inspire further research in mathematical model and epidemiology. Okay, so that concludes our session.